Good morning to all. Today we are going to discuss about the topic interception. In our unit 1, the course outcome of this topic is on the successful completion of this course. Student will be able to build the knowledge of various components of hydrological cycle that affect the movement of water in the earth. So the course outcome with correlated the program outcome 1, then program outcome 7 and then program specific outcome 1. The interception can be defined as that segment of the gross precipitation input which wets and adheres to above ground object until it is returned to the atmosphere through evaporation. So the precipitation streaking vegetations may be retained on leaves or blades of grass, flow down the stream of plants and becomes steam flow or fall of the leaves to become part of the through fall. The modifying effect that a forest canopy can have on rainfall intensity at the ground, the through fall can be put to practical use in watershed management schemes. The amount of water intercepted is a function of the storm character, the species, age, and density of prevailing plant and trees, the season of the years. Usually, about 10 to 20% of the precipitation that fall during the growing season is intercepted and returned to the hydrologic cycle by evaporation. Water losses by interception are especially pronounced under dense closed forest stands as much as 25% of the total annual precipitation. Additional information given in table, so it includes some data on interception measurement obtained in main from a mature source fair stand, a moderately well stocked white and grey birch stand, and an improved pasture. So see the weekly average precipitation catch of standard US Weather Bureau type rain gauges located in a fire stand, a hardwood stand, and a pasture during the winter of 1965 to 1966. So see the measuring dates, weekly average precipitation catch in equivalent rain like a sphere, bridge and pasture, then percent interception by forest cover, fire and bridges. So weekly wise, so 7 days differentiated, so 9 and then 16. The here they are calculated the data. So see the illustrate the general time distribution patterns of interception loss intensity. Most interception loss develops during the initial storm period and the rate of interception rapidly approaches zero. Therefore, potential storm interception losses can be estimated by using Li is equal to S plus K into Et, where Li is nothing but the volume of water intercepted inches. So S is nothing but the interception storage that will be retained on the foliage against the force of wind and gravity, usually varies between 0.01 and 0.05 in K is equal to the ratio of surface area of intercepting leaves to horizontal projection of this area. E is nothing but the amount of water evaporated per hours during the precipitation period in T is equal to time in hours. So see the rainfall interception based. So the curve will be changed in different manner. So depositing of rainfall input in terms of interception, depression storage, infiltration and over land flow are occur. So totally we can add frontal interpretation. So that is called rainfall input. So see the interception, depression storage, infiltration and overland overflow supply. So is based on the assumption that rainfall is sufficient to fully satisfy the storm system. Yes, the following equation was designed to account for the rainfall amount. Li is equal to S into 1 minus C power minus P divided by S plus K into E T. Like where P is nothing but rainfall and E is the base of natural logarithm. Note in equation 1 and 2 that the storm time duration T is given in hours while Li, S and E are commonly measured in or mm. It is important to recognize that forms of vegetation other than tree can also intercept large quantities of water. Grasses, crops and shrub over have leaf area of ground area ratio that are similar to those for forests. So intercepted amount are about the same as those for forest, but since some of this type of vegetation exist only until the harvest, their annual impact on interception is generally less than that of the forest area. So see the summarized some observation that have been made on crop during growing season and on a variety of grasses. Observed percentage of interception by various crop and grasses. So the vegetation time intercepted in percentage level comments. So the crop, alpha, corn. So these are the intercepted percentage. So water can apply off in the 30 minutes. So period in arrows. So A is nothing but the values. Okay, the above one is the values rotated by nearest person. Data for table were obtained from 2, 4 and 5, where grass height vary up to about 36 inches. So see the factor that serve to determine interception losses: precipitation type, rainfall intensity and duration, wind, atmospheric condition affecting evaporation. So the snow interception, while highly visible, usually is not a major loss since much of the intercepted snowfall is eventually transmitted to the ground by wind action and melt. Interception during rainfall events is commonly greater than for snowfall events. In both cases, wind velocity is an important factor. The importance of interception in hydrological modeling is tied to the purposes of the model. Estimates of loss to grass precipitation through interception can be significant in annual or long term models, but for heavy rainfall during individual storm events, accounting for interception may be unnecessary. It is important for the models to assess carefully both the time frame of the model and the volume of precipitation with which one must deal. So see Li is equal to S plus K into Et, whereas Li is equal to S into 1 minus C power minus P divided by S plus K into Et. The equation 1 and 2 can be used to estimate total interception losses by for detailed analysis of individual storm. It is necessary to deal with the aerial variability of such losses. General equation for estimating such losses are not available. However, most research has been related to particular species or experimental plot strongly associated with a given locality. In addition, the loss function varies with the storm character if adequate experimental data are available. The nature of the variance of interception versus time might be inferred. Otherwise, common practice is to deduct the estimated volume entirely from the initial period of the storm, like initial abstraction. So, using the following equation developed by Horton for interception by ash and oak tree, they estimate the interception loss beneath tree. This tree for a strong having a total precipitation of 1.5 m. For ash tree, Li is equal to, so here inches in 0.015 plus 0.23 p. Here we can add substitute the value p, then we got 0.36 inches. So for ash tree, 0.03 plus 0.22 p, then here we can substitute p values is 1.5 n, so 0.36 inches. And the true fall based, a number of relationship for estimating true fall for a variety of forest type have been developed. So determining factors for true fall quantities include canopy coverage, total leaf area, number and type of layers of vegetation, wind velocity, and rainfall intensity. The aerial variability of these factors result in little or no true fall in some location and considerable throughfall in others. In general, prediction equation for throughfall must include measures of canopy, surface area, and cover as prime variable. An example of a throughfall relationship for an eastern United States or woodland forest follows. For the growing season, TH is equal to 0.901 p minus 0.031 n. Whereas for the dormant season, TH is equal to 0.914 P minus 0.015 N, where TH is nothing but true fall inches, P is equal to total precipitation in, N is equal to number of storms. So these are the reference material. Thank you.